All right, so we've worked through problem one and moving to problem two. This is really more of a section one question, so I am not going to spend time in this video working through it. If you have questions about the solution or how to work through it, I'm happy to take those. Uh, Send me an email, schedule a Teams meeting with me. I'm happy to walk you through it. I'm not going to devote time in this video to that because I think it's a waste of time. Instead, let's move on to number three, which is about expected utility. We're told that the only thing that you care about in life is your grade in microeconomics. Your utility function is natural log of that grade. So this is a convex function, means you're risk averse. You know that the probability that you get a grade of m sub 0 is 1/3, and the probability you get a grade of m sub 1 is 2/3, where m sub 1 is greater than m sub 0. So you have a better chance of getting the higher grade, right? Question one asks us, alternatively, you can be guaranteed a grade of m sub c. You're indifferent between receiving m sub c and receiving m sub 0 or m sub 1 with the probabilities above. Solve for m sub c. So this is sort of like a certainty equivalence question, which is saying like, well, hey, how much are you willing to sacrifice to from your expected value so that your expected utility is the same as the certain utility you receive, or excuse me, the utility you receive with certainty from this non-risky outcome, m sub c, right? So we're not solving for certainty equivalency, but it's definitely related to that concept. Let's go ahead and set up the question, right? So we have 3.1 here, and we have this probability of receiving m sub 0, and we have a probability of receiving m sub 1. We know that m sub 1 is greater than m sub 0, and we have a utility function, which is a function of m, and it's this risk averse function here, natural log of m, right? And so we're trying to figure out what this m sub c, what is this, the value of this? Well, what are we willing to accept with certainty? We'll give up some points, but we don't, we really don't like playing the lottery. We don't like the uncertainty of our game. It's it's too stressful. We really don't want this bad outcome where we get a lower grade. So we'll probably accept this m sub c that's somewhere between these 2 points. That's not as good as the expectation that we get from the from playing the lottery, so to speak, right? But because our utility function is because we're risk averse, our utility function is convex, we're probably willing to take some sacrifice to avoid the uncertainty altogether, right? So that means we need the utility that we get from the certain outcome to be equal to the expected utility that we receive from playing this lottery, right? So this is how we would set up the problem. U sub, whew, that's a bad m. Let's try that again. M sub 1. Okay. All right, so let's plug in our utility function first thing. Natural log of m sub c is equal to 1/3 natural log of m sub 0 plus 2/3 natural log of m sub 1. We need to isolate m sub c, so inverse log function we need to apply to both sides. M sub c is equal to m sub 0 to the 1/3 times m sub 1 to the 2/3. I'm not going to discuss the math in detail here. You guys should understand how to solve for these algebraically. And we get this nice solution here, right? Now let's move on to 3.2. We'll use a new fancy color too. So the grading scale changes, such that the probability that you get a grade of 0.9 m sub 0 is 1/3. Same probabilities, but just a worse grade. Same probability of the better grade, but it's worse too. And your difference between receiving this new certainty parameter, this new grade with certainty, and receiving, basically playing the lottery, right? So write m sub c as a function of m sub c tilde as a function of m sub c. So we know that 3.2. We know that, what we're being told here is that m sub c tilde is the same thing, from this equation here. We know that we can just multiply these outcomes, right? This relationship's not going to change. That this is true, right? So what we can do is we can pull out this 0.9, because this is just like, this function here is a homogeneous function of degree 1, which means we can just pull out constants that are multiplied by the different parameters, right? So this is the same thing as 0.9 times m sub 0 to the 1/3, m sub 1 to the 2/3. And this right here, this looks awfully familiar because we got it from when we defined m sub c. So we can replace this part with m sub c, they're equivalent. So, and in doing so, we'll have written m sub c as a function of, or m sub c tilde as a function of m sub t. So this is our solution. And this has to do with risk aversion parameters. I know that in class, so we didn't talk about this class of function. We talked about the constant absolute risk aversion functions. We did not talk about constant relative risk aversion functions, even though we talked about the relative risk aversion parameter, right? So just as a reminder really quickly, the risk aversion, absolute risk aversion parameter, right? That's just, oh, I forget the notation that we used, but you guys can look it up in on the slides. So that's the absolute risk aversion parameter, and then relative risk aversion parameter is almost the exact same. We're just multiplying by the wealth term. And so the natural logarithm, it's a special, it's a special case of a constant relative risk aversion. Which just means I have the same risk aversion at different all these different levels of wealth, basically, right? So that's why this function, this math works out really nicely, is because the natural logarithm just has these nice properties where this relative risk aversion is constant, right? And I can go into that and show you mathematically what that looks like. I'm not going to spend time to do that. Hopefully this really, it's most important to understand this process because we didn't talk about constant relative risk aversion functions when we cover this material in class. So this is something that David put a little bit more emphasis than I did. So yeah, we can move on to the next question. I'm going to go ahead and clear this. And let's look at the next question. There's a probability of 1/3 that you get a grade of m sub 0 plus x. And so we have the same probabilities, but all of a sudden we have this parameter that x gets added to m sub 0 and subtracted from m sub 1, and you can choose x, right? You get to pick this thing that reduces the variance of the random variable. It reduces the dispersion of the random variable. So what x maximizes your expected utility? So just thinking through this problem a little bit, I want to talk about the intuition because that is the purpose of these videos. So if you guys remember, in class, I'm going to make this really big so I just hopefully don't screw it up. Ooh. Speaking of screwing it up, that's a terrible line. We talked about like graphing these utility functions. It looks something like that, right? So this is like the utility derived from x. In this case, it's actually m, so I'll go ahead and write that. And this is m that we receive. So like what we've been doing so far is we're playing this game where we're playing this lottery where I can get m sub 0 or I can get m sub 1. And then, of course, when we think about the expected utility from playing the lottery, so like we're connecting these two together. This is a surprisingly straight line. I'm pretty pleased with that. And we have the expectation of, playing the game basically at 0 and 1. I guess that's the notation I'll use. And actually, I'll tell you what. This is going to be like, it's not going to be right in the middle because that would be 50-50 chance of either outcome. It's actually going to be, we have 2/3 chance of getting, we have a better chance of getting something over here. So like my expected grade is somewhere from playing the lottery is something like this. And the utility I get is actually this level right here. Expected utility of m01. Looks like that. Okay. So, we pay this utility penalty because we have this convex utility function. But then, so what this question is asking is saying like, hey, look, we're not going to change the probabilities at all, but we could, we could increase this score obviously this isn't fixed. We're trying to figure out what bounds we're willing to accept. We can like really reduce. We can make the bad outcome less bad, but the good outcome gets less good. And so, we'll have some new expected utility. Like maybe it's better, even though our expected value is lower. Actually, the utility that we're expecting to receive will be greater because we get to sort of dodge out on all the risk involved. Involved with the lottery, sort of mitigating risks. We can mitigate risk, and we'll pay some penalty because we expect a lower grade. But like, hey, look, at least the bad grade isn't going to be nearly as bad, right? And like, just think about like the distance you're traveling here from these two, right? It's like we got rid of a lot of bad utility, and we only gave up like a little bit of good utility. That's sort of what's happening when we're trying to figure out what this x is. So we have to maximize x, and then we have the expected utility. Right, so we get 1/3 probability that we get m sub, we actually need the natural logarithm there, don't we? Natural log of m sub 0 plus x plus 2/3 natural log of m sub 1 minus x. And so that's what we're trying to maximize, right? Right, so we need to find our first order conditions, right? This is an optimization problem. So we need to take the partial derivative with respect to x. Utility with respect to x, we're going to set it equal to 0. And that's going to be, all right, we have to use the chain rule to calculate the derivative here. So it's going to be 1 over m sub 0 plus x times 3, right? Let me double check this. I'm pretty sure this math's right. Plus 2 over chain rule, the inside, the derivative of this function. Yeah, okay, 2/3, right? And then, right, this is set equal to 0, and then we just need to solve for what x is. So we can think about this as m sub 1 minus x is equal to 2 times m sub 0 plus x. And then recovering the x term, we get sub 1 minus 2 m sub 0 all over 3. And that's how much we're willing to give up of x. Well, we give it up on the good case, but we gain it in the bad case. So this is the x that maximizes our expected utility. It can be defined as a function of m sub 1 and m sub 0. And obviously the probabilities are baked into our expected utility function, so they're reflected in these 1/3 and 2/3 that are applied to either case. All right, cool. So that's the problem. If you guys have any questions, let me know.